Our final set of exceptions to the usual octet rules are thinking about Lewis structures that can form where atoms have less than an octet. There are, in this case, rather than it being a specific, rows in the periodic table, it's actually just a handful of particular elements that tend to do this. And those elements are boron, beryllium, and aluminum. So you're almost always going to see it with these elements. So coming back up here. So boron, beryllium, aluminum. These are generally the three elements where you're going to see things form with less than an octet structure. So that's one thing. That's one nice thing with this. The less than an octet is not very common and is limited to just essentially these three elements. Let's go through an example of a Lewis structure. So one compound that can form, again with a combination with a very electronegative element here, is BF3. So this is a molecular compound that can form between boron and fluorine. And let's go ahead and draw the Lewis structure of this. All right, so boron, this is not an element we've used a lot, so this only has 1, 2, 3 valence electrons. So it has two s electrons and one 2p electron. Right, so we have 3. Fluorine has 7. It's the halogen over here, so it has 7 valence electrons. All right, so that gives us a total of 24 electrons. All right, and so we're going to draw boron with our fluorines attached, and now we'll add our lone pairs, and that gives us our 24 electrons. So if you count this up, 2, 4, 6, 8 on each fluorine, times 3 gives us 24. So we're done. This is the structure of boron trifluoride. We're not quite done, though, actually. So we'll talk a little bit more about this. But this is an example of sort of the opposite of what we saw in the last video. All the fluorines are happy. They have their octets. And generally, fluorine, again, is one of these that doesn't break the octet rule. But boron, on the other hand, only has 6 electrons around it. So, yeah. We can calculate the formal charges here. And if we do so, we will calculate that everything has a formal charge of 0 in the structure as is. Now, one thing we can do, we sort of have competing things going on here. We can get boron with an octet. So if we share these electrons here, we could end up with a double bonded fluorine, and then the other fluorines are single bonds. And this still has the correct number of electrons. This is a resonance structure. And again, we could repeat this. There's 2 additional resonance structures where the double bond could be on the fluorine on the bottom or the fluorine on the right instead of the fluorine on the left. We're not going to draw all those out because the analysis is going to be the same. Now let's look at our formal charges on these fluorines. Again, you can double check me on these if you don't trust my math here. But these 2 fluorines have formal charges of 0. But if we look at this fluorine right here, all right, so fluorine has 7 valence electrons normally. We've got 4 electrons in lone pairs plus 4 that are shared. So that gives us 7 minus 6, which is plus 1. So that gives us a positive formal charge on fluorine. And for boron, again, it usually only has 3. There are 0 non-bonding electrons, but 8 bonding electrons, which gives us -1. And so we get a -1 formal charge on the boron. All right, so we're sort of like between 2 things, right? It's either we want to minimize the formal charges, which gives us the less than octet structure, as we see on the left, or we give boron an octet, but that requires us to put a positive formal charge on the fluorine. Now, as it may be difficult to guess, but the actual structure is some mixture of these things. So the fact that we can move this formal charge is sort of shared because we're gonna have 2 more resonance structures where the double bond is in a different spot on the different fluorine atoms. That positive formal charge on fluorine is trying to get shared with the other 3, so it's not quite as bad as it seems at first. But you get something that's sort of in between the single bond and the version with the double bond. All right, so this is the most important. This version with the less than octet structure, because we've minimized the formal charges, but this version also contributes as well. Okay, so some other examples of molecules that will have less than octet structures. Again, these are going to involve those elements that I talked about that you can practice with, is something like aluminum trihydride, AlH3. This is going to have a structure like this, and that's all the electrons we have. There are only 6 electrons because aluminum contributes 3. The 3 hydrogens contribute 3. We get 6 electrons. And in this case, we can't form double bonds because we don't have any lone pairs to work with. So this is a pretty simple example of another structure where aluminum happily forms this molecule. It's not a super stable molecule. It's pretty reactive. But again, aluminum only has 6 electrons here. So, and we could look at some examples with beryllium too. But this gets across the point. There are some exceptions where we have less than octet. They're rare, and they are limited to basically these 3 elements. Now, just on a final note, this is our last of the exceptions we're going to talk about, but hopefully helps you realize that the conception of Lewis structures, it's just a model that we use to understand bonding. The electrons don't know the octet rule. They don't know these rules that we follow to draw structures. They're just trying to find the lowest energy. And these are the sorts of structures, the things that we've been drawing, that give the lowest energy configurations of the electrons being shared between atoms, forming bonds. So that's just one thing to remember. Don't hold the Lewis structures as being too important. They're important. They're a useful tool. I think that's the best way to think of them. They're a tool for us to help understand bonding, and they work for a very large number of molecules. These rules are tried and tested. So despite these exceptions that we're talking about, there's really only talk about them as exceptions because there's not tons and tons of them. So for many of the molecules we care about the most, all the rules that we learned at the beginning of this chapter apply really well, and particularly to organic molecules. So when we're thinking about things involving carbon, that really follows the octet rule and the other rules that we've talked about with Lewis structures. And those are molecules we care about a lot. So molecules that are of interest in biology, in biochemistry, in organic chemistry, a lot of these rules work quite well. But it's just a model, right? What's really happening underneath is that there are electrons and they're waves and they're in orbitals, and these orbitals are mixing together. We'll talk a little bit more about that in the next chapter as well. But this concludes this section about exceptions to octet rule. We'll have one more section from chapter 8 where we're going to be looking at the lengths and strengths of bonds, and then we'll be moving into molecular geometry at the end of the week. So that's it for this section.